All right, so for the next set of slides, what I'm going to do is introduce some theory regarding semi-Markov decision processes. And this is going to be essential to understand the next two papers that we're going to discuss. So these are going to be papers about hierarchical reinforcement learning. And the bottom line is that the theory underlying this is pretty much based on this notion of semi-Markov decision processes. Okay, so let me first say a few words about hierarchical reinforcement learning. So I'll start with an example. So in reinforcement learning and Markov decision processes, so far what we've done is we say that there's a set of states, and then in each state we would like to execute some action, and then this will influence the environment, which will get into another state, and then we'll choose another action, and so on. But if you think of certain tasks, let's say when you drive, and now let's say that we want to design a self-driving car, well, it might make sense to modularize this reinforcement learning task. So we don't have to think that necessarily everything has to correspond to some low-level actions, but we can think of it at a higher level. And then so for instance, if you're driving a car, then often you've got a high-level goal where you simply want to reach some destination. But then to reach this destination, you might have to go through certain waypoints. So that might be some locations, like you know that you need to reach a certain town and then another town, and then you'll reach your destination. So that might be town A, then town B, and then town C, right? So these are sort of like sub-goals. And then in terms of reaching town A, well, as you drive along the way, you might at some point see a red light, therefore you need to stop. And then you might reach an intersection, and then you need to do a turn. Okay, and then you might be on a road where there's a slow driver and you want to overtake this driver, right? And then depending as well if whether this is your final destination or not, maybe at the end you would like to park the car as well. So here we can think that, you see, we can further decompose those goals into some subtasks, and then those subtasks will in turn become really just a sequence of really low-level actions. So at the end of the day, what do you do when you drive a car? You do one of three things, right? You're going to press the brake pedal, you're going to press the gas pedal, or you're going to steer the car, right? These are really the three things that you're doing. And so here we can think of this really as a hierarchical task, again, because we've got the high-level goal decomposed into some sub-goals. These are decomposed into some subtasks, and eventually we've got our low-level actions. But you see, again, when you're planning to reach some destination, you don't start planning by thinking, you know, precisely at every second whether you're going to press the brake pedal or the gas pedal and so on, right? You just think at a higher level, and then depending on what sub-goal and what subtask you're currently accomplishing, right, then you're eventually going to decide what you need to do in terms of pressing the brake versus the gas pedal and so on. And yeah, so here you see this is an example, but then in a lot of other complex domains, like there are some examples with respect to video games as well, where you can think that in a video game there's a mission, and then that mission you can break it down into some subtasks, and then this will turn into some lower level behaviors and so on. If you consider robotics, then there's something similar as well, where there's the low-level controls, but often, you know, with the robot, it could be that if it's a mobile robot, it needs to reach a location. In terms of reaching that location, it might need to open up some doors and therefore grab some things, and then maybe carry an object as well. So then there's lots of subtasks that one might want to induce. Okay, so basically, this is something very appealing, and in fact, there's been already a lot of research, so decades of research on hierarchical reinforcement learning, but it's still something that is not easy to accomplish. But in any case, in order to understand how we could achieve something like this, where maybe we could divide into some sub-goals and sub-tasks what we want to do, then we're going to use the notion of semi-Markov decision processes. Okay, and here, yeah, okay, let's get straight into semi-Markov decision processes. So, well, in fact, no, let me start with semi-Markov processes. So a semi-Markov process, here we can define this with a set of states as well as some transition dynamics. But the difference with what we've seen before, whenever we talked about a Markov process, is that now I'm going to have transition dynamics where there's going to be states, but also some notion of time that I'm going to capture with tau. So here tau is going to indicate the time to the next transition, or in other words, the time that the environment is going to spend in the current state before it changes to a new state. So this is interesting because before we always discretize time, and then we just said that, okay, there are some time steps, and then at every time step there might be a transition. But now here we're going to make these time steps more explicit. We're not going to assume that they're all roughly the same amount of time. So some time steps might be longer than others. And then so concretely, it would look something like this, right? So we might be in a certain state. We're going to remain in that state for some period of time tau. Then we transition to another state S prime. Then we remain in that state for another period of time tau prime. But that period of time might be smaller than the previous one. And then after we transition, then in S double prime, we're going to remain there for another period tau double prime. And that might be also different, and so on. Okay? So the idea is that with a semi-Markov process, we include the notion of time. And here, it's still Markovian in the sense that the next state depends only on the current state. But then we also want to capture the notion of time. And then the time spent will vary with respect to each state. Yeah?
So the key thing here is that we can decompose the transition dynamics to be conditionally independent on the current state?
Yes. So, okay, it depends how we formulate this. At least the way I've written it here, which is a classical way of writing this down, is that, yes, here it would still just depend on the current state. And then based on the current state, I would have a distribution over the next state. And then I would also have a distribution over how long it will take before the next transition happens. Okay? Now, another way of formulating this could be that we say, well, since we introduce time, let's make this more symmetric and have both the state and the time that we condition on. And then it is possible to obtain an equivalent process that is going to be a continuous time process. But now what happens is that it's not going to be Markovian, at least not in a strict manner, simply because at any given time, what happens at the, let's say, an epsilon amount of time later, would obviously depend on what is the current state, but also the time. But then the time, we want to take into account how long we've been in that state. And therefore, we need to remember when was it that we switched to that current state before. So we need to sort of look at a history of previous time steps. So here, I guess I shouldn't use the word time steps because it would be something continuous, but I have to look at the history of my which state I was in and when, and then from that perspective, it would look like it's not Markovian. But then if we don't make things condition on time per se, and we write it in this way, then it is Markovian. But in any case, the convention is that we call that semi-Markovian. Yeah. Any other questions? Okay. Good. So now we can formulate, based on this, a semi-Markov decision process. So it's analog to a regular Markov decision process. We're going to have states and actions. We'll have a transition model. Now here we use both S prime and tau, just like in our semi-Markov process. And then we'll have a reward model that has an expected reward for every state action pair. There's going to be a discount factor. It can be less than 1 or it could be equal to 1, which means that there's no discount really. And then we could also have a horizon that might be finite or infinite. Okay? So it's very similar to what we've seen for a regular Markov decision process, but as you can see, the main difference is that now we introduce tau, and this will have some impact on how we compute values as well as optimal policies. Okay, so just to give you a concrete example, where do such processes arise? Classically, in operations research, it was in the context of queuing theory. So there's lots of queuing problems that are still very important today. The classic type of problem would be that you consider, let's say, a retail store, and then there might be queues or lines, let's say at the cashier or at the counter for customer service, and so on, right? So most retail operations will deal with customers where you form a queue to get whatever service, whether it's just to pay, whether it's to get something else, okay? But now let's say that we've got a retail store with 2 queues, and just for the sake of arguing, let's say that there's one cashier, so there's going to be a queue for the cashier, and then there's one customer service desk, and then there's going to be a queue at the customer service desk. But now let's say that on a given day, for whatever reason, there's only just one employee working in that retail store, and that employee now has to deal with both queues. Okay? So then there's an interesting question about, you know, there's 2 queues, who should be serviced when? And in other words, at any point in time, then this employee will essentially service a customer either from Q1 or Q2. Here, Q1 and Q2 could correspond to the customer service queue and the cashier queue. Okay? And then the state of this semi-Markov decision process is going to be essentially the number of customers that are currently in each queue. Okay? Now, based on this, we can imagine a transition model where here, roughly speaking, is going to be a distribution over the arrival and service time for customers in each queue. So in other words, there's going to be customers that might arrive in the store and then might get into the queue, so that's the arrival time. And then the employee is going to service customers from each queue, and then that will also take some time, and that time might vary, right? So here you see the transition model. In fact, what is very important is this notion of time, how much time is going to take to service the customers, but also for customers to arrive at different points in time. So here there could be all kinds of mathematical models that could be used. I didn't bother writing any specific one, but you should get the idea. Now for the reward model, here we could consider the expected revenue of servicing each customer, but then also we might want to remove from that some expected cost that's associated with the waiting time. So here, obviously, I mean, the waiting time is the time that the customers are waiting in line, and I mean, that might not impact any revenue directly, but some of the customers might end up leaving, or they might get angry, they might not come back to the store, and so on, right? So there is at least some hidden costs associated with the waiting time, and then we could have a model for that. So this could be our reward model. Okay, so this is a classic example where semi-Markov decision processes are typically used, and now the question is the same as for regular Markov decision processes. How can we find an optimal policy so that we can maximize our rewards? Okay, so here we can also formulate as an objective a value function that will correspond to the sum of expected rewards. But then the main difference is that you see, since, okay, if we consider a scenario where rewards are discounted using a factor gamma. Now we need to take into account how long it will take in between different transitions. So perhaps we get a reward each time that we've got a choice of choosing some action and applying our policy. But then that reward might come in later if it took a long time before we were able to execute that action, or it might take a smaller amount of time. So like in the case of customers in a queue that we're servicing, right? So if you earn some reward or some revenue from servicing customers, and then if it takes you less time to service some customers, then perhaps those rewards come in faster, and you don't want to discount them as much. So here, the idea is that we'll want to discount those rewards, but then we need to use an exponent that takes into account the amount of time. And then so perhaps here at the if decision point, right, then there might have been an amount of time passed that corresponds to the sum of all the previous periods up to tau I. So then we would add up all those periods of time, and that would give us the time at the if decision point. Okay? So then we might want to discount by gamma raised to the power of ti. Okay? Yeah, so that's the main difference, because we're going to have this here. And, but otherwise, you see, once you can compute a value function with respect to different policies, then the optimal policy is simply going to be the one that has the highest value in every state. Okay, so to find the optimal policy and the optimal value function, we can use Bellman's equation. It's very similar to the one for a regular Markov decision process. The main difference, again, has to do with discounting. So here we're going to add up the immediate reward plus an expectation over future rewards. And here you'll notice that instead of just having the discount factor gamma in front here, I have the discount factor gamma inside the summation, because it will depend how long it takes before I make a transition. Right? So I want to discount those future rewards based on how long it takes before I receive them. And so that's why now the discount factor is pushed inside the sum. And then here it will have an exponent, tau, that corresponds to the amount of time. And that's stochastic, so it depends on how long it takes before we get to switch to the next state S prime. Okay? So yeah, so that's the main difference. It's not a big difference, but it's still a difference. And now let's say that we want to do reinforcement learning. So perhaps what is the simplest algorithm that we've seen is the Q-learning algorithm. And then so we can do a Q-learning update that's very similar to what we've seen before. Again, the difference is simply with respect to the discount factor. So here, at any point in time, well, actually no, at any decision point in time, what will happen is that we're going to receive from the environment the next state S prime, some reward R, and also we'll be able to observe how long it took to transition, so the amount of time tau. Right? So we actually receive three things: the next state S prime, the reward R, and the amount of time tau. So now we can use tau simply to apply the discount, and then otherwise it's the same update as before. So here I'm just showing you, the simplest type of Q-learning update that in fact assumes that we've got a tabular representation, but then you can generalize this to using a function approximation like a neural network, and then we can turn this into a DQN if we want, where we would simply use this discount raised to the power of tau. Okay, so it would work in the same way. And then if we want to use some gradient update, this can be done as well. So basically, wherever we used to just have the discount factor gamma before, now we're going to replace that by gamma raised to the power of tau. Okay, any questions regarding this? Okay. Yeah.
So I think there are some relation set semi-Markov process and the Markov process. So MDP can be considered as like each time step is one. So if we just treat as that, the semi-SDP MDP will become MDP.
Yeah, very good point. So yeah, so here if we want, we can think of the semi-Markov decision process as a generalization of a regular Markov decision process, where here, if we simply set tau to be equal to 1 all the time, then we recover just a regular Markov decision process. Yeah.
So you can replace T tau times step with the Markov decision process with S for each one. So it doesn't change in this time period. And it's like the
Oh, I see. Yeah, yeah. So we can, yeah, we could also well, okay, so here we introduce tau as time. The most general way of introducing it is just to say that this is going to be something continuous. But in some scenarios, in fact, in hierarchical reinforcement learning, it will make sense as well to consider tau that's only integers, so natural numbers that are positive. And then as a result here, if it's still discrete, just like natural numbers, then it is possible to then just say that, okay, we're back to just having decision points at every time step. And now it's just that we want to have some distribution that would say whether or not we're going to remain in that same state or not. This still provides a generalization, because if you do this trick of saying I'm going to discretize time again, and then it's just that now maybe at the next time step I'm going to stay in that same state and so on, then you're kind of forced to use a distribution that would at every step would say that, okay, the probability that I remain in the same state is the same. So in order to satisfy the Markovian assumption. And here part of the reason why we call this semi-Markovian is precisely because we could have distributions with respect to tau that are not necessarily like following an exponential that would be sort of like independent of what has happened before. So normally like the exponential distribution, right, the time to, I guess, the next event, right, is independent of how long it took before. But here we could formulate some distributions where it could depend on that. So that's why this still provides a generalization. Yeah. Okay. Good. Okay, now let's come back to hierarchical reinforcement learning, because I introduced Semi-Markov decision processes, and I told you it would be useful to provide us with some theory. But what I did is simply explain that in the context of operations research, where there was no notion of hierarchy. But now, if we want to introduce some notion of hierarchy, there is a framework called the option framework that has become popular over the years. And then in that framework, the idea is that we formulate hierarchical reinforcement learning as a semi-Markov decision process, where we're going to have actions that are really options, and then an option is really just a temporarily extended sub-policy. Okay? So if I just go back to my first slide, yeah, right here. So here, I have perhaps a semi-Markov decision process that happens to have some actions that corresponds to reach A, reach B, and reach C. And then reach A itself now is going to be a policy or a sub-policy. And then it happens to have as actions turn, overtake, stop, and park. And then these, in turn, we can think of them as, again, some sub-policies that have as well some actions, brake, gas, and steering. Okay? So that's how we can think about this. So here there is a hierarchy, right? So each circle in this graph, right, would correspond, if you want, to some sort of semi-Markov decision process that has some actions that correspond to sub-policies at a lower level. Okay? And now, because the actions are going to correspond to sub-policies, the idea is that this sub-policy might take an amount of time that varies to execute it, right? So here, I have a goal of reaching a certain destination. Maybe I want to drive to Montreal, for instance, and then to do that, I need to go through Toronto, then eventually go through Kingston, and then go through Montreal, right? Now, to reach Toronto, that might be my first goal, and then that will take some time. It depends on the traffic and so on. And then because the amount of time will vary, right, then I cannot assume that I'm going to have time steps that are all equal, right? So this will not just take one time step, it will take a certain amount of time, and perhaps I want to model that too. So that's why then a semi-Markov decision process will provide us with the right tools to understand what are the implications of taking the time component into account. Okay, so yeah, so basically, as we're going to formulate our hierarchical Markov decision process as a semi-Markov decision process where the actions are options, and here options is just a name really for some temporally extended sub-policies. Okay, so the idea is that inside the semi-Markov decision process we have an action space, right? So if I just go back here, we said that there is a set of actions, but now each one of those actions is going to be called an option. It's just another name, it's a fancy name, but it reflects the fact that, okay, we can choose between those different actions. So we've got an option to choose between each one of them, right? And then those options, they're going to take a certain amount of time because they're going to correspond to policies or sub-policies lower into our hierarchy. Okay, so now I'm going to denote by A bar an option, and then it will have a corresponding sub-policy. I'm going to call that pi bar. And then the sub-policy, at some point, it should terminate. And now, depending on how we formulate this sub-policy, there are many ways in which we could trigger the termination, but the simplest way is just to declare that there's going to be a set of states in which, when we reach them, the process just stops. Okay, so this will be the end of the option. So yeah, typically an option would be defined by a policy or a sub-policy pi bar, as well as some termination condition, which for the sake of this example, I'm simplifying to just say it's going to be a subset of states that when I reach them, it means that the sub-policy has ended. And concretely, you see in the example before with driving, if my goal is to reach location A, perhaps my states refer to what are my possible locations, and then when I reach location A, then yes, I've completed that sub-goal, so this would trigger the termination of that sub-policy. Okay, so with this, now what we would like to do is define some transition dynamics. So I'd like to define the distribution over states that can be reached when I execute my action or sub-policy A bar when starting from state ST. Okay, so here again, yeah, this is a sub-policy. So we are in a current state or some initial state. When we execute A bar is going to take a certain amount of time that might vary. So that's why we have tau here that indicates the amount of time it might take. And then at the end, we're going to terminate in some state, st plus tau. And here, if we terminate, at least with this example, it should be that this state is part of my terminal states. Okay? So now I can estimate this distribution using this expression here. So what I would do is essentially look at all the possible trajectories or all the paths that would go from st to st plus tau. And I can unroll these trajectories by simply here looking at all the consecutive pairs, computing their probabilities, and then summing the probabilities of all those trajectories. Okay? So that's essentially mathematically what one would do to obtain this. But at least we know in theory that, you see, when we have a sub-policy, right, then we're going to end up in some terminal state. It will take a certain amount of time tau, and there is a distribution over those terminal states as well as the time tau. And then if we want to estimate that, then that would be the expression. Okay, so that's for the transition dynamics. Now with this, we also want to associate some reward function. So here, I'm going to generalize our notion of reward. So before, we said that the reward would only depend on the current state st and the action. Now I'm going to make it depend as well on the final state st plus tau, as well as the time it took tau. Okay, so this will become important on the next slide. It's a slight generalization. It doesn't change anything really to the problem, so it just means that now we have more flexibility in terms of defining our reward. But when I use this definition, then what I could do is say that the reward of the option A bar corresponds to the sum of the rewards that I would obtain while executing that option. And here, because I've defined those rewards to really be the expected rewards, then here I'm going to compute the sum of the expected rewards as I execute my option A bar. So when I execute this option, then I'm really executing the sub-policy pi bar, right? So I'm going to obtain an immediate reward for being in state st, executing the action prescribed by pi bar. Then I'm going to add to this the future rewards. So here I would discount this, and now I'm really working one time step at a time, so I'm discretizing in the usual way. But then the idea is that I'm going to unroll this up until tau time steps. Okay, so until I reach essentially the state st plus tau, and then so all the rewards that I would obtain along the trajectories that go from st to st plus tau, I'm going to add them up, and I'm going to take their expectation, and then I'm going to summarize that into my reward function. Okay, so that's the idea. So yeah, so for an option, we can, well, there is some implicit distribution as well as an expected reward that correspond to these things mathematically. Okay, so then with this now, what we can do is also adjust Bellman's equation to work with options. So again, options are really just like actions, but they have some period of time that they take to execute, and then the resulting state at the end, there will be a distribution, and then so this expression, right, would come from this equation that we have right here. Okay, so the idea is that you see at one level in my hierarchy, right, then I get to choose some options or those sub-policies that correspond to pi bar. And then when I do this, then I can work with this Bellman equation to optimize my choice of options. And then so I would use this transition dynamics as well as the rewards that I just explained in the previous slide. And this is again Bellman's equation. Now the main difference is that I've pushed the reward inside the expectation, because now my reward depends on S prime as well as tau. So, but that's really the only difference. Okay. So yeah, so that's for Bellman's equation. I can also do Q-learning here too. If I want to do Q-learning, what I would do is again take well, the immediate reward that I would obtain from executing the sub-policy corresponding to the action A. And now because it's a temporally extended action, so this option, it's really an option, so then I would need to sum together all the rewards that I would obtain along the trajectory when I execute this option, and then I can plug this in here. Okay? And then after that, I need to discount by gamma to the tau because it took tau time steps. And then I also have the discount gamma to the tau in here too. Okay, so that's the main idea. Okay, any questions? Yes?
You used, I believe, the notation G when you were talking about Monte Carlo estimation of this. Is that coincidental or is it this?
Yeah, very good point. So yeah, so I'm using G because it does correspond to a Monte Carlo trajectory of executing the policy. So it's the same as a rollout, but now it's a rollout of the option. Okay, so that's why I'm using G, just to be consistent with the same notation. And I think someone else had a question here, or it was the same question. Okay, good. Okay, so in that case, yeah, let's stop here. Yeah, so these were all my slides, and then this should help you understand the next two papers that we're going to discuss regarding hierarchical reinforcement learning.